there was problem 3, which was the one on what you might call cosmic morphology. In other words, what are the different possible qualitative behaviors of cosmos, a simple spherical Friedman, dust-filled cosmos. Many people, so basically you're asking for the different possible solutions of the Friedman equation. And many people only gave, for some reason, part of the solution. Like, there's one of the solutions, probably the most well-known one is the de Sitter solution, which is one that starts, if you consider the whole space-time from beginning to end, it starts at infinite size. You know, it's just geometrically the hyperboloid you get by embedding in 5-dimensional Minkowski space. It's a hyperboloid like that. And so if you slice it up like this, in this one case, there's actually not a unique slicing, unlike the cases where matter is present. But if you slice it up like this, then you would say, or in fact any reasonable slicing that's compatible with the spherical symmetry, you would say that at early times it was infinitely large, then it contracted down, reached a minimum size, re-expanded, and went back out to infinite size again. But many people, for some reason, said, well, we could start here, or we could start here, or we start here, and only go towards the future. Of course, that's true. They're all solutions of the Einstein equations, but they're not the, in some sense, the full story. They're in some sense artificially truncated. It's just like I could take Minkowski space and I could chop out a hole from it and say that was a solution of the Einstein equations. But everyone would regard that as artificially done. And in the same sense, it's kind of artificial to just give part of the space-time. So if someone asks for the solution, what they almost always would mean is give the maximally extended space-time. You know, if it hits a singularity and it can't continue, that's one thing. But if you just decided to start time at some, like maybe, I hope there's no born-again Christian that will be insulted by this, but some people believe that the universe, the world may have begun in 4,000 years ago or something like that. Was it 6,000 years? Anyway, a few thousand years ago. That would be, I suppose, an argument for artificially truncating, but short of that, I can't think of any reason. So that was one comment. In other cases, perhaps there's a genuine physical doubt about what you should give. The Schwarzschild solution is an interesting case. In this case, in these situations, there's really no ambiguity, because if you take a moment of time and then take the initial data on that hypersurface, which is a sphere, then you can propagate it unambiguously forward and into the future and into the past. And you get, in this case, this hyperboloid, or in another case, you get this, this universe that if you propagate it towards the past, you hit a singularity. If you propagate it towards the future, you also hit a singularity, and so on. And these are, in some sense, the maximally extended solutions. Cases like Schwarzschild are more interesting, because the Schwarzschild solution, in this case, you have a Cauchy surface, although we haven't defined this, but many of you will be familiar with the term. That is, we have a surface such that knowing the behavior of the solution in the neighborhood of that surface fully determines it in the whole future and in the whole past in a unique way, unless you just choose to stop evolving at some point. But as long as you continue that I want to keep evolving as far as I can, then it fully determines the solution. Schwarzschild is an interesting case, the black hole solution, because we start with, if we view it this way, like we know the metric outside the black hole. If all we start with is the metric outside the black hole, there's not necessarily a unique way to extend it inside the black hole, because you don't know what might be there. And in that case, people often use the so-called Kruskal-Shekaris extension, which is, you might have seen, I won't bother to draw it, but it's got another asymptotic region to it and so on. So you go into the black hole, and then you go through this handle or wormhole-like thing, and then you come out to another asymptotic region. That's also the maximal extension that you get by analytically continuing the metric, but it's not physically required in some sense. It could have been something else. There might not have been another asymptotic region there, and so on. But I can imagine there are cases where there's a genuine physical ambiguity in how you extend a solution, but these are not that case. In this case, you just set up data at some moment of time, and that really uniquely, determinism takes over, and you get the unique future and past. So it's not, in some sense, crazy to have truncated the solution, but it's a little artificial in this setting. Another comment, one or two people had trouble taking the variation of the action. That's something you should learn as soon as possible, because it comes up all over in physics. So if you're uncomfortable with the notion, with how to do that variation, then you should make sure you become comfortable with it. This comment I can skip. Comment on this, I think it was problem 4, where it was asking you to use this volume time, this kind of unimodular time, as it's sometimes called, which is the 3-volume related to the proper time by this equation that d tau. So in doing the variation there, a couple of people didn't realize that you should vary dt freely in the same way that we varied d tau freely when we were doing the original Friedmann equation. And for the same reason, exactly the same reason. They both have a similar physical content. They just represent the local metric. So I won't go through the argument again, but just as you don't want to hold tau fixed at the initial and final endpoints, you don't want to hold t fixed at the initial and final endpoints. Except in the last part of that problem where it asks you to do precisely that and ask how it would have changed the set of solutions. And then, I guess one other comment on this same problem 2, which was the one, problem 2, which asks you to, the two Einstein equations, the one that came from varying d tau and the other one that came from varying a, asked you about the relation between them, and you saw that this one, the equation coming from varying a and the equation coming from varying d tau, were almost equivalent to each other. Well, not almost equivalent, but that this one almost was a consequence of this one, but not quite. So one way of, if you say that this equation is lacking a little bit that this has, then one way of exhibiting that, the most convincing, is to find a solution of this equation that's not a solution of this equation, because that proves that this has some extra force that this one doesn't, has extra information in it. So that's sort of I think the nicest way to do it. And in that case, the solution was this static cosmos, which solves this. You just set a dot equals 0 in this equation, but you find that in general it does not solve this equation. Oh, and there was an interesting thing I had never thought of. Most people did what I had in mind, which was to take the equation that came from this and differentiate it with respect to tau and show that you get a multiple of this equation. But a few people came up with a clever idea of differentiating this equation with respect to a and showing that you get this equation. And that looks like it works, but actually it can't, because we know there's a genuine ambiguity. And why did it fail? I guess the reason it failed is that a is not a good coordinate, right? Tau is a good coordinate on the whole space-time. As it changes, it moves you through the space-time without ever doubling back. But in certain situations, like this situation, a is not a good coordinate anymore, because a has the same value up here as it has down here. And in particular, right in the middle, where it's not changing, it's not even locally a good coordinate. And in the extreme case of this pseudo-solution, that solves the first equation, but not the second, a is a terrible coordinate, right? Because it only has the same value everywhere in the space-time. So asking how something varies when you vary a has no meaning in that particular space-time. So that's an interesting subtlety. So if you wonder why it didn't work, why you seem to get exactly this equation, which is what people seem to find, the answer must be this: that you're pretending when you form a d by dA, you're pretending that a is a good coordinate, which it's actually not. So secretly, it's the same division by zero that goes on when you try to derive this from this, in the case where a dot is 0. Okay, so let's continue on with where we were, just a sort of boring calculation that we just started, not too long, fortunately. But let me set it up and then see if there were any questions that came up, or else we'll just, about how it's set up, otherwise we'll just continue with the calculation. So we're considering a massive particle. We want to find the trajectory of the massive particle in a fixed space-time by varying the action and setting the variation to 0. So in the picture, as we have some world line like this, and we're considering the variations in which, say, 1 and 2, points 1 and 2, in which we vary the world line arbitrarily in this. If we want to get the equations of motion, we vary it arbitrarily, subject to fixing the endpoints. However, it's actually very useful to let even the endpoint vary, but we're still only interested in the action. We'll see why it's useful in a second, but we're interested only in the action between these two, of this finite portion of the world line. And we had written down the action, and we had got to, I guess, so it's convenient to take, obviously, the minus m out, and work temporarily with the variation of minus s over m, and I guess we proved that it was the integral. Is this exactly where we were? Oh, and the one thing I stressed, there were the two variations, the two types of sort of d's go in the story. One is sort of dp or dx, since we're using coordinates now. So there's a sort of dx, which is just as in dx d lambda or dx d tau, the change along the world line, right? And then there was, so here's one world line, here's a varied world line. So there was dt, and then there was the variation that takes you from one world line, dx, and then there was delta x, which I used for the variation that takes you from one world line to the neighboring world line. And we saw that these two kinds of variations commute. That was the thing that we're going to need. The formal, I won't write down the same equations we had before, in which we introduce another parameter along with lambda, and then this d is variation with respect to, is partial derivative with respect to lambda, whereas this delta is, which is the traditional thing for varying the world line, is partial derivative with respect to this auxiliary parameter that labels which world line you have. Using that, you can convince yourself that the two variations do commute. Okay. So, and that we'll use. So we got 1/2, and then there was this whole integral, this whole integrand, which I haven't written, so maybe I should write it out again, which was minus g mu nu dx mu dx nu to the minus 1/2. Did I take out the d lambda? I think at the moment I had left the d lambdas in. And then we know that you never really need to write the d lambda, because it's just an arbitrary parameter along the world line, and so it must drop out, and it does. It's easily seen that it does drop out. But just keep it for the moment. So we get minus G mu nu. Of course, these indices G mu nu are contracted with these, not with. I mean, I use the same index again, but they shouldn't be mixed up. So we just want to vary this. And then since I haven't divided through by the d lambda, I guess that should be right. Right, okay. So now we just have to go through, turn the crank. So it's, what do I have? So this thing here is, of course, this thing here was d tau d lambda. That's what we started with, basically. So this is d tau d lambda. This square root thing was d tau d lambda. So its inverse is really just d lambda, is just d lambda d tau, if you like. So it's d tau d lambda inverse. And when we come to vary this, we get two different kinds of contributions. One of them comes from varying x because the metric coefficients are depending on the location. So when you move the world line, you get they change. And then there's, of course, just the direct x this is an implicit dependence on x. This is an explicit dependence on x, if you like. That also. So when we vary this, we get. This becomes d g mu nu times dx mu d lambda dx nu d lambda plus, now what have I've canceled out the minus signs here. Okay. So it becomes that plus, and then we have to vary each of these two, but by symmetry, that's just twice what we get by varying the first one. So it's g mu nu of x. Now here's where we use the commuting. We have to vary dx mu d lambda multiplied by dx nu d lambda. So this will, if we write this out again, it's 1/2 the integral d lambda d tau from this term, and then we have to multiply this. What's this dg mu nu? Well, that'll be just that changes because of the dependence on x. So it's just partial what? Partial alpha g mu nu of x times the variation of x alpha times this dx mu dx lambda d lambda dx nu d lambda plus 2 g mu nu. Here's where I use the commutation that I can interchange the variations d and delta, and so I have d by d lambda of delta x mu dx nu d lambda, right? Oops, this should have said, what happened here? This should have said d tau, of course. Something is messed up somewhere. Oh, I left out the d lambda here. Okay. So now, if you look at the d lambdas, they all cancel, right? There's two. Oh no, I've drawn the same. What have I done? Yeah, that's right. It's correct, yeah. So there's 2 d lambdas in the numerator and 2 d lambdas in the denominator, so I can just take them all out. Okay. and I can import d tau instead. So I can just rewrite it. So I can leave a d tau outside, convert it into an integral over d tau, and then divide through by d tau squared. And so it is equal to 1/2 the integral with respect to d tau of, so now we have partial alpha g mu nu dx delta of x alpha dx mu d tau dx nu d tau plus 2 g mu nu. So I'll leave this for the moment. D by d tau of delta x mu and dx nu d tau. Okay? So all I did was basically swap the d lambda by the d tau. Now what am I going to do? Well, remember how you proceed in getting these variational equations. You want to isolate something multiplying the variation of x mu, so that you can claim that since the variation of x mu is arbitrary, you can set that coefficient to 0. But here we have its derivative. So to get rid of the derivative, of course, we do an integration by parts. So let me, however, since to save writing, let me make a shorthand notation. So I'll call it u alpha, this tangent vector, now taken with respect to the parametrized curve where tau, proper time, is the parameter. I'll just call that as it's usually called, the four velocity, u alpha. Okay, so that's a shorthand now. So now this becomes u mu, and this becomes u nu, and this becomes u nu. Okay. So I have to do an integration by parts, and so I would then get now what do we have? Partial alpha g mu nu delta x alpha u mu u nu plus let me bring the 1/2 in here. Then I don't have to write this 2 here. Okay. And so it's d by d tau of everything else, which is g mu nu variation of x mu u nu minus, so minus what? Delta x mu times d by d tau of g mu nu u nu. Okay. Does that look right? And what is this bit here? This is just d by d tau of something, so we can do the integral. That's the point of the integration by parts. And we just get g mu nu u mu, say, delta x nu evaluated at the endpoints 1 and 2. And then what we're left with is the thing that's giving us the equation of motion. And to go from 1 to 2, d tau of, so what do we have? 1/2 dx delta x alpha partial alpha g mu nu u mu u nu, and now minus this bit again has 2 pieces in it, so delta x mu So we have to differentiate first u, so we get, that's du nu d tau times g mu nu, minus, where we differentiate this, is it's delta x mu u nu. We have to differentiate that, so that'll be partial alpha. It's the variation of g mu nu along the, this time along the world line instead of to the adjacent world line. G mu nu dx what alpha d tau, but this is really, this is u alpha. So if I didn't mess up the algebra, let me write this, let's give this a name. So this is g mu nu u mu delta x nu. I'll call it minus the integral of d tau, the variation of x alpha. And this coefficient, because it represents a kind of acceleration, it generalizes when you do the Newtonian, the non-relativistic derivation. This, what would come out here would be the acceleration of the particle. So I'll just call it A alpha. And A alpha, so if you rearrange the indices appropriately, you get that A sub alpha is equal to minus 1/2. Tell me if I made if this is how it should come out. I'm just copying instead of looking over at the other board. Mu nu plus, now I'm going to introduce a shorthand notation that's probably familiar to most people, where I represent partial derivatives by commas. Hold on. G mu nu alpha mu nu. Okay, well.
So maybe I wasn't listening, but you went from delta tau to d tau?
No, I shouldn't have done that. What did I have? If I wrote delta tau, it's just bad.
Tau right there.
This?
Nope, next one down. Yeah, front of the integral. Front of the integral.
Front of the integral. Oh, this was a mistake. That should be d tau. That's right. Should be d tau. Right. Other. Okay. Yeah. Any other corrections? Okay. So this should be this. So this is. Why am I getting? Did I leave? Oh, I left out the second derivative, right? Plus g mu alpha d squared. Oh no! So let's look at this term. I know I wrote it down somewhere. Well, I'm sure it's here somewhere. I just wrote it. Oh, here it is. Yeah. So this is this du d tau. Of course, u itself was dx d tau. So this du d tau I can write as d squared dx. Was it alpha or mu there? Alpha, I guess. Right. I'm just using that du d tau is equal to d squared x d tau squared by definition. Okay, so that's the result. So we can simplify it. Now it only remains to simplify this. So it's again We just want to make it look prettier. So for the purpose of making it look prettier, let me do this a little earlier than I was going to. So we want to make two definitions. We want to define, which everyone I think is familiar with. First of all, we define the inverse. This means G alpha beta inverse, so to speak. In other words, this is just a matrix that solves G alpha beta, G beta gamma equals delta alpha gamma, right? So that's this very familiar, I think, definition of the raised, what turns out to be the components of the metric tensor was raised indices. And the other definition I want to make is the usual, to use this, the G, both with upstairs and downstairs indices, to raise and lower indices. So if you have any expression that has the form x alpha, then you define, say with the raised index, you define the lowered index to be G alpha beta x beta. Which I'll also define. I'll be using this because it will look weird to you at first, maybe, but it actually is convenient in some cases. There's no actual need to distinguish alpha and beta here because it's a symmetric thing, and only one of them can be contracted. So I could write this, and I will, as G alpha alpha x alpha. It doesn't mean the convention here is that you only sum on indices, one of which is upstairs and one of which is downstairs. So you couldn't think that it meant to sum on this. And it's convenient to do this because it shows you see, your eye doesn't have to see that the beta has turned into an alpha. Anyway, I like to use this notation, so I'll use that in some cases. The main thing is that you raise and lower the indices by contracting with the appropriate kind of metric. So I think that's all very familiar. So having done that, now we can ask what is A alpha with the index upstairs. So I just have to raise the index alpha. Where were we? Oh, yes. So here, let's look at this term first. All I had done was lower the index mu here, right? If I used this other notation, I could have even called this G alpha alpha, dx alpha. Then when I raise the index back up, it'll just become dx alpha. It'll just go back to where it started, so to speak. So it'll be dx alpha d tau squared, d squared x alpha d tau squared. And then there's this other term, which we have to work out, which is 1/2, if I restore what u was, dx mu d tau times dx nu d tau, times what? Of course, I said it in words, but I've also used the convention, might as well write it here, for completeness. I've also used the convention that x alpha beta, for example, that just means partial beta x alpha, which in itself, of course, means partial x alpha, partial little x. I shouldn't have used x, but anyway, little x beta. So that's the notation we're using. So now what's here? So we have something multiplying u mu u nu, and what is it? It's so let's. Oops, I didn't finish with. No, I did. Yeah. So it's g mu nu alpha plus g alpha mu nu minus 1/2 g mu nu alpha. So this we give the name, well, not quite. I can't quite give it the name yet. I was going to call it the Christoffel symbol, but I have to do something before I can do it. So first of all, obviously the 1/2 cancels here, so this becomes 1/2. But now what about this term? It's not, we could just leave it like this, but it's not particularly natural because, you see, this is multiplying something that's inherently symmetric in mu and nu, whereas this thing is not symmetric in mu and nu. So I could just as well put here alpha nu comma mu instead of alpha mu comma nu. They'd both be equally valid for this equation, but it makes them non-unique. So it's conventional, and it's obviously a natural thing to do, to symmetrize this and call that the relevant quantity. And so if we symmetrize this, I can replace this then. It's not literally equal to, but when it's multiplying these two, I can replace it with 1/2 g mu nu alpha plus the 1/2 is from this, and the other two 1/2 is from the symmetrization, alpha mu comma nu plus g alpha nu comma mu. And you shouldn't have let me get away with it, but remember I raised the index alpha here, so I needed, when I raised this one, it was already lowered, so it went back. But this one, this alpha is lowered, so I need to put in I need to raise it explicitly. Okay, so now this line is right, and then this line, so we actually are going to include that. Okay, and this combination here is this whole thing now is given the name of Christoffel symbol, and it's written as G alpha mu nu. Okay. Oh, this one should have been, should be, yes. Which one did I mess up? This one, first line, this one is a minus sign, is it? Yes, this one is a minus sign. The one that's not symmetrized is the minus sign. The one that I didn't have to symmetrize is the minus sign. So therefore I can write this finally in the form, just summarizing what we've done. I have A alpha is equal to d squared x alpha d tau squared plus gamma alpha mu. Now I'm going to pull the same trick. Alpha mu mu dx mu. If you don't like this, you can feel free to, change the names of the indices. Where gamma alpha, and we just have the expression for it here. So gamma. Okay. Now, what about any questions on this? More questions? Yeah.
You said that symmetrizing was conventional, but then you also said they're not equivalent.
Oh, no, I said they are. Well, they're not the same array of numbers, right? So if I defined gamma alpha without the symmetrization, it would be a different quantity. And in other contexts, it might be the wrong. I mean, it turns out that this is the most important quantity to work with in general. But if all you ever cared about was writing the geodesic equation, then it would make no difference. You could have used any combination of those two. Because the antisymmetric part drops out as soon as you multiply it by this dx mu, dx nu. But on the other, one other comment, as I said, this gamma has a more general meaning. It has to do with the covariant, as you probably know, or some of you will know, it has to do with the covariant derivative. It's the expression of the covariant derivative in a coordinate chart. And if you want to get it in that sense, then you better symmetrize. Then you can't just go and use anyone. So what we've done here is actually, if you like, once you know this other application of what this Christoffel symbol is used for. And you ask, how can you compute the Christoffel symbol? If you could take this to be its definition. I mean, that is its definition. That's a valid definition for it. But if you need to compute it in any given case, it's often easier not to plug into this definition directly. Because look here, all the indices, you have 4 times 4 times 4 indices. You have, even though it's symmetric here, you have 40 different components to work with, and it's complicated. If you just go back and start from the geodesic equation as the least action equation. So in other words, just write out what S is, carry through the derivation just as we've done it, but in the particular case that you have at hand. Then that'll often give, and then make sure you do this relevant symmetrization. Then it'll give you gamma. That's often a more efficient way of computing gamma than going back directly to this general definition. Okay. I think we may see an example of that. So what I want to say, now I want to go back to the term we left out, which was somewhere behind this or behind, no. Yeah, this was the term we left out. So let's go back to what the variation of S was. So that I have to take I think I've hidden some of the relevant things. But if you take my word for it, so we start, I divided through by M. Now I multiply back through by M, and I'll get the variation of M will be G mu nu M mu U mu delta X nu minus, and this is what we had before, d tau A, let me write it like this, doesn't much matter, M times G mu nu A mu delta X nu. Okay. So that's the final answer, given these definitions. So the important thing is that in addition, the equation of motion, obviously, that we're going to get from that is that A is 0. Which, if we write out what it says, it says that this thing equals 0. So basically, it gives you the second derivative, time derivative of x. Well, I wanted to make a couple of comments, but it gives you the second time derivative of x, but it doesn't give, it's a little different than what you're used to, because what you're used to is seeing just some function of x here, but not the derivatives of x. So this is, as it were, a velocity-dependent force. But aside from that, it's telling you that when the space-time is not flat, or when your coordinate system is not adapted to the flatness, it's a curved coordinate system, you'll see some sort of velocity-dependent forces. These are, in another context, more limited context, these are called Coriolis forces or inertial forces, sometimes they're called. But otherwise, it just looks like an F equals ma equation. It's just that F is a little bit different from what you're used to. We'll see, well, yeah. We'll come back and look at this in a second in the case of a weak field approximation. And then we'll see how it goes over to the familiar Newtonian form and that limit. But I wanted to say, yeah, so let's, for the moment, focus on this term, which comes in when you don't fix the endpoints. So you allow the variation of the endpoints. Then the variation of the action is not 0. But if we consider, for example, holding the initial endpoint fixed and varying the final endpoint, then the rule is that the variation of the action gives you the momentum of the particle. So if you like, it's a definition. And so we should we want to say that in that situation, delta S, so this is the situation where we don't vary the initial endpoint, but we do vary the final endpoint, and we limit ourselves to trajectories which solve the equations of motion so that this term goes away. Then what's left over is ds is equal to, by definition, p mu delta x mu. If you like, you could say plus a sort of term, I'll just represent it as e d tau, where e represents the equation of motion. So it's something that vanishes if the equation of motion is satisfied. That's the general, I don't need this. That's the general character of the variation of the action. So that's zero if the equations of motion hold or satisfied. The same thing works in field theories. And when they're satisfied, then it reduces to a surface term, or in this case, an endpoint term. And the coefficient of the variation in x we call the momentum. So what this teaches us, this is the definition of the momentum. But what it teaches us in this case is that p mu, well, it's just whatever is here, is equal to g mu nu m u mu, u nu, I put it, which by our rules of raising and lowering indices is just m mu. So if you like, it's p, this is this formula familiar from special relativity, and it's still valid here, is that the momentum is just the mass times the forward velocity. The forward momentum is the mass times the forward velocity. So we call this momentum. It's what comes, it's conjugate to variations in the position, so it's called momentum. If we vary the time, that's the zero component, that's conjugate to variations in time, that's the energy, and so on. If we were to do a rotational variation, it would be a term in the angular momentum. So, a couple of comments. First of all, a couple more comments. I think I already said this. The equation of motion is second order, as you would expect. Here's the equation of motion. I thought I wrote that somewhere. So here's the equation of motion. The vanishing of this, it's second order, as you would expect. I already said that these forces are the velocity dependent to a certain extent. But you could call, since this no other force is acting on this particle, it's just moving in a pure gravitational field, it's natural to think of these as, in some sense, the components of the gravitational field. So we could call this the gravitational field. But notice, as I said, that it depends, that the force that comes from them depends in part on the velocity. And the analog here is the Lorentz force. There's a lot of often a close analog between gravitational forces and electromagnetic forces. And so you're used to velocity-dependent forces in the case of the Lorentz force. Right? So electromagnetic force is like that. It has a component that doesn't depend on the velocity from the electric field and a component that does depend on the velocity from the magnetic field. So something similar is happening here. And then what else? Oh, another comment is that notice what happened. We started with a curve which we could have parametrized arbitrarily and did, but had we stuck to that, we would have, if we had stuck to an arbitrary parameter, we would get a very messy equation. And that's basically because that parameter is arbitrary. It has no physical meaning. By re-parameterizing it, you can make the equation look messy. But what happened is that that parameter got replaced by proper time. And so it's written in terms of proper time that this equation holds. What was the other? Oh, the last comment is that this notion of, although the action I wrote down wouldn't directly work for I mean, the question is, what would happen if we went back to a massless particle, say a photon, or an old-fashioned neutrino? Then this equation here wouldn't make sense because of the square root. You'd be taking the square root of something that was vanishing at the solution. And, of course, the square root is not differentiable near zero argument, so you wouldn't be able to carry out the variational derivative this way. Nevertheless, it's true that this equation of zero acceleration is true also in the massless case. So it holds also for mass equals zero. And we can, in fact, there's different ways to derive it, but the way we'll probably do later is you can replace this by a less physical but more practical action principle. Less principle? Yeah, in a certain sense, less physical action principle, which is quadratic, doesn't have the square root, and leads to the same equations of motion. But the main thing is that this also holds for zero mass. So not only massive particles, but massless particles always move along geodesic if you define geodesic not by extremizing the arc length, which doesn't make sense for a massless particle, but by the straightest path, which is by setting to zero the acceleration. And later we'll see when we come to define covariant derivative why this means a locally straight path. Okay. Any more questions? Any questions on that? Yeah.
So going back to the symmetrization thing, so you had the two terms and you symmetrized the mu and the nu in the second term.
Right.
Is there any reason why we wouldn't, like, what would happen if we kept the anti-symmetrization too? So we had the Christoffel symbol, and then we have an extra term.
Which is antisymmetric?
Which has the anti-symmetrization of the mu and the nu.
So as far as the geodesic equation, nothing would happen. I mean, as far as the, what am I trying? As far as the this definition of the acceleration here, nothing would happen.
So we would get the exact symmetrization motion?
Yeah, because you can see it, right? Suppose I add to this. So let's write out the equation of motion again. It's a d squared x alpha d tau squared plus gamma alpha. I'll make them distinct since this is an issue of symmetrization now. Now suppose you replace gamma by some gamma hat alpha mu nu, which is gamma alpha mu nu plus some, I don't know, some skew, some sort of so this thing is now antisymmetric in its two indices instead of, so it's like that. It's got an instead of symmetric. So then if we replace this by gamma hat, it'll just read gamma alpha mu nu plus S alpha mu nu dx mu d tau dx mu d tau. But then, of course, because this is antisymmetric in mu and nu, and this is symmetric, that would drop out.
Except gamma, so I mean, it wouldn't be fully antisymmetric, would it? Because if you...
No, it wouldn't. It would be only this other term. But
No, I mean, if we just do the anti-symmetrization of those two, then when we replace, if we swap mu and nu, the first term doesn't change at all, and then the second term, the next two terms would swap signs.
I'm not sure what you're asking me to do. You can't arbitrate. I'm not saying you can do any symmetrization at all. I'm saying that you won't change the equation of motion if you do a symmetrization. But you said, what if we kept some of the antisymmetric parts?
Well, what I'm saying now is, so we have, so what gamma hat is gamma plus S mu nu
right.
alpha.
Right. Where S alpha mu nu is equal to minus S alpha nu mu. That's the antisymmetric.
I'm not seeing that.
Oh well, no. It's just a statement that you could split any tensor into its symmetric and its antisymmetric piece. So you just take any t mu nu, and you write it as t mu nu plus t mu plus t mu nu minus t nu mu. So I just added it and divided by 2. This is here I just added and subtracted t nu mu. So this is an obvious identity. This piece is symmetric, and this piece, well, I need another 2 here. But
Yeah.
that piece is antisymmetric, right? That's all. That's all I've done. And then I've noticed, this is true for any array, any matrix, and then I've just noticed that this part drops out. That's the sort of filled out form of the proof. So I've just added 0 to that equation. That's all. If you go home and think about it, it'll become obvious to you.
I understand most of it. Just one. I just need to work something out of my head.
Yeah. Okay. But as I said, it would affect the definition of this, and it would affect the definition of the covariant derivative, which involves this. But as far as this equation of motion is concerned, in fact, if you make M have an antisymmetric piece, you've introduced what's called torsion in the covariant derivative, or the connection, as it's often called. But that's getting ahead of the story. So this is saying the torsion would not influence the equation of motion written in this form. Okay, so now remember we talked about a little bit last time. We talked about reference frames and clocks and so on. There was something sort of left hanging. It wasn't obvious that it left hanging, but it was the redshift. We haven't yet discussed the redshift. Why I've put that off because we don't know yet what the Newtonian limit is. We don't know. The redshift is something that's easy to analyze in an approximation in which you're nearly in the flat space, in the special relativistic limit. Some of the heuristic arguments that go with it are in that limit. So we need to first, before we can understand the redshift, at least in this way of getting at it, we need to understand particle motion. We need to understand see, we said that this was the gravitational field in a certain sense, but we need to know what components of it correspond to the Newtonian potential and so on. That we can learn by looking at motion in a weak field, slow motion in a weak field. Of course, that in itself is important because for the solar system dynamics and so on, to a first approximation, or that's what you have. You have slow motion relative to the speed of light in a relatively weak field. The other thing I wanted to say, I think I did say it, but let me just emphasize it, is that these components of the gravitational field are not curvature. They're not just picking up on the curvature of space-time. They're picking up both on the intrinsic geometry of space-time and on the choice of coordinate system. And that goes back to the remark I made a long time ago, that gravity, as it's experienced, phenomenological gravity, is not only an expression of curvature, or not even mainly an expression of curvature. It's often an expression of the relation of our reference frame to the inertial reference frame. Okay, so now let's look at the weak, now that we have the equation of motion, let's look at the weak field and slow velocity limit. This is almost Newtonian, you might call it quasi-Newtonian. So motion in a weak field at slow velocities. We could now go back, we could take this equation of I think that in Schutz's textbook he does something like that. We could just take this equation of motion and analyze it in that way. But it's actually easier, as I was just saying before, it's easier, instead of doing that, just go back to the action and ask, what does the action look like in the situation that we're talking about? And then when we see what it looks like, you'll be able to immediately identify the terms with the action you're used to from non-relativistic mechanics. That, I think, is a somewhat easier way of getting out at this order, or leading order, the weak field motion in a weak field. So what is weak field? Weak, that means almost flat, right? And slow velocity, of course, means just what it says, but I'll write it as, so this is approximately flat. So that means G alpha beta is going to be approximately equal to the flat space metric, eta alpha beta. And velocity, this means the three-dimensional velocity now. So the norm, however you want to say it, the norm of the three velocity, which I'll just call V for the moment. But I don't mean it as a four vector. I really mean the magnitude of the three-dimensional velocity should be much, much less than 1. But now I'll write it as much less than the speed of light, because since we're interested in this limit, it becomes useful to reinstate the speed of light explicitly. Okay. And the flat metric, so that means dt squared, d tau squared, ds squared, is approximately equal to, I'm writing it again because now we have, see where we want to put the C, I'll put it here. The question is, do I choose to define this as a distance or a time? I've chosen here to define it, this arc length, as a distance. And of course, I'll use the usual convention when writing some formulas that the zeroth coordinate is the time coordinate. Now, these two assumptions, weak field and slow velocity, are related to each other. In fact, if you have a strong field, it's obviously not consistent to assume slow velocity, because even if you start with slow velocity, it's not going to last. So what does weak field mean? It means that so imagine that there's some sort of central force or something like that, like the sun or something, that's causing the field. And so then we know that the strength of the gravitational potential is like gm over r. These are just order of magnitude estimates. It's of the order of gm over r, which, since I'm working with kappa, I would write it kappa m over r. They're of the same order. But the other thing is to know is that if you think, for example, of the virial theorem, that this gravitational potential up to a factor of 2 or something, in the case of a bound state, is also comparable in magnitude to v squared. So in doing this, we make this rough this assumption that this is roughly the case. And as I say, it will be consistent if you start with slow velocities and remain in a weak field. So I'm doing this because we want some measure of first-order effects, second-order effects, and so we're going to regard this as being of the same order, v squared, as being of the order of the gravitational potential. And so I'll assume, I'll call this thing epsilon, which is at the same time the order of v squared and the order of the gravitational potential, and we'll assume that it's much less than 1. Maybe I needed v squared over. If I want to call, I guess I have to call this epsilon c squared, if I really want to keep c. And then the assumption, however, is that epsilon is much less than 1. That's our approximation. Under that approximation, now what we want to do is write out, go back to the expression for the, expression for the action, which I didn't quite write out, so I'll write it out again. And we want to we want to approximate that expression for the action under these assumptions. First, let me mention, so if epsilon is 1, that's in some sense the first I don't know what you call it, post-pre-Newtonian order or something. I mean, it is the Newtonian order, but it's post the zero field order. Okay, so now in making this approximation, we'll use the following. So now consider the spatial. So this is the spatial components of the metric. So that's by definition dx k. What did I say? The spatial component of the velocity. That's by definition dx k dt. But we want what actually will often occur. I'm not saying this one. I want to claim that we can freely, to the order we're working at, replace dt by d tau, proper time. So why is that? So we know that dt, d tau, this is just special relativity, is this gamma, right, which is 1 over 1 minus v squared over c squared. So that's equal to 1 plus order v squared over c squared, which is order epsilon. But if you so as long as this is multiplying something which itself is small, which it will be, because it's going to be multiplying this gamma, we can replace the d tau by the dt. I'm not actually sure if I need that for this derivation, but in general you do need that. So keep that in mind. And now let's write out the action for the particle. Well, the action was just d tau, right? So we know that the action was equal to the integral of minus m d tau. And d tau was just the square root. I think I better put, now I'm really, yes. I think we want the action to have if we want it to have the usual units, which is energy times time, I better put the c squared into its definition, since we've given d tau the units of time. Okay. So all we have to do is evaluate d tau. So let's start with the expression for ds squared. That's minus c squared dt squared plus 2g0k dt, right, dxk plus gjk dxj dxk. Here, as always, j and k are running from 1 to 3, the spatial index. Therefore, this is equal to minus d tau squared times c squared. So d tau squared, using these conventions that I've just used for s. So therefore, d tau squared, I just have to divide by minus, oops, I left out something here. I mean, I wrote the wrong thing, more accurately. I should have written g00, right, dt squared. So now dividing through by minus c squared, we have d tau squared is equal to minus g00 over c squared dt squared plus all the rest. I'm just now it becomes minus. I have to change the sign. G0k dt d tau d what? dt over c squared dx k over c squared plus gjk over c squared dx. I think I'm on a minus sign here, right? Now let me multiply through and divide by d. Let me take out a factor of dt squared. Okay. So this will go away. This will go away. This will become dxk dt over. And what do I do with these? I don't know why I wrote c squared twice here. I have one extra c squared. So I want g0k. I want to apportion these. One c I'll put with the g0k, and the other one I'll put with this. And then this will become minus gjk. This will become dxj dt dxk dt 1 over c. So, or if I write it all out again, it's and divide through by dt squared, then I get d, just for convenience, then I get d tau squared over dt squared is equal to, this is the main result, minus g00 over c squared minus 2 g0k over c times vk over c. I replaced dx dt by v minus gjk over times vj vk each over c. Okay. Now let's look at. So this is just trivial algebra, which I made a little look harder than it is, but it's just trivial algebra. Now let's look at what kind of approximation we can make for these terms. First of all, it's zero order. So let's look first at this term. So we saw that eta 0, 0, I mean, we know, since this normalization we're using, that eta 0, 0 is minus 1, or in this case, minus c squared, with the c restored. So let me write g0, 0. So minus eta 0, 0, which is easier to work with, is plus c squared. So let me write minus g0, 0 is equal to c squared plus a correction, which is small by assumption. That's our definition. I'll call that correction 2, 5. Just an arbitrary name for the moment. But you'll see in a second why the 2 is when this name suggests that it will be the Newtonian potential, which it will. And the 2 is just so that it'll be normalized in the usual way. And where we assume, this was our assumption, that all the deviations from flatness are of order epsilon, so phi over c squared is order epsilon. The second term we can look at, now let's look at this term. This g0k over c is of order epsilon. It's also small. It also represents a deviation from the flat space value, which in this case is 0. So in this case, it was the flat space value plus a correction of order epsilon. In this case, the flat space value is 0, so that it itself is of order epsilon. And V over C, what order is it? Well, we said here that V squared was of order epsilon, or V squared over C squared was of order epsilon. So this is order of epsilon to the 1/2. Okay. So that means that this thing taken together is order epsilon to the 3/2, which is of a higher order than the other terms that we're keeping. So we can just drop this term. And then we can ignore this at the order that we're working. And then at the same order, this thing is itself order epsilon. This is order V squared over C squared. And this thing, again, it has a flat space value, which is just 1 and 0, ones and zeros. And its correction is then, by assumption, order epsilon. So we also have, we can assume, we have assumed, that GJK is delta JK plus order epsilon, since it's, again, the gravitational field effect. But that means that this whole thing here will be order, there'll be the constant term, which certainly will contribute at order epsilon. But the corrections to the constant term, this order epsilon bit will bring in order epsilon squared. So that's even smaller, so we can neglect it too. So the net effect is to just replace this by delta JK. So now if we make those substitutions, then what do we get? dt squared. Can people see this? dt squared d tau squared is approximately equal to, keeping only these lowest order terms, we had minus g00 over, and we defined that as c squared plus 2 phi. So if we divide by so it's 1, well, c squared plus 2 phi over c squared. Mine.
dt or d tau on top or bottom? Or is this there?
Here I've divided. Here I've just, did I not? Oh, I switched these two. You mean? Yeah. Thanks. Yeah. Right. Then we have minus, then this term went away, and this term is just b squared, minus b squared over c squared, which obviously is equal to 1 plus 2 phi over c squared minus b squared over c squared. But what we want is d tau dt. Then we can integrate that with respect to dt, and it'll make it look like the usual, take the familiar form. So we just need to take the square root of this. So that's just 1 plus half this. These are the two small terms. So it's 1 plus half of this, which is phi over c squared, minus b squared over 2c squared. Or if I multiply through by dt, that gives us d tau. Then remember, the action, now remember, was minus m times the mc squared times the integral d tau, which I can write as d tau dt times dt. So it's just the integral dt of minus mc squared times this expression, right? Which is equal to minus mc squared. Somehow I have the impression I divided and multiplied by c squared unnecessarily, but anyway, plus phi, minus phi, sorry, plus mv squared over 2. So that's our final approximation. I don't know what we left out, but I think it was order epsilon to the 3 halves. Anyway, we left out something which is of smaller order than the terms we're keeping. So now look at this. I mean, that looks very familiar. What is this? Except for the term, this minus mc squared, which is not going to affect the equations of motion because it's just a constant, as long as we assume that the mass doesn't change, as the particle doesn't change along its world line. Aside from this term, this is really a minus e dt term, if you like, in the action. But it doesn't matter what we call it. It doesn't affect the equations of motion. What we have here is just the usual Lagrangian for a particle moving in a potential energy, in a potential field, phi. This is the kinetic energy, and this is the three-dimensional velocity, of course. So when I write v squared, it means, it's defined to mean delta jk dxj dt dxk dt. That was our definition. Okay, so this is just the ordinary flat space kinetic energy, and this is just some term which, if you trace it back, came from G00, and it shows you that G00 plays the role of the Newtonian potential. Therefore, the conclusion is what I just said, that phi is equal to the Newtonian potential, the gravitational potential of the Newtonian theory. We can write this another way, just going back to how we define phi. Remember, we defined phi as equal to minus G00 in terms of minus G00, which is the same as the absolute value of G00. So we can say that the absolute value of G00 is approximately equal to c squared plus twice the Newtonian potential. So what we've learned here is, first of all, that we recover the Newtonian theory in this appropriate limit. And second, what's important for what comes next is we've learned that the Newtonian potential should be read off from the time component of the metric in terms of this equation. Using that, then we'll be able to, now we can start talking about the gravitational redshift, how much, because we want to know how much redshift there is, say, for a beam of light that propagates to between different heights. We want to relate that to the change in the Newtonian potential, and now we know how to relate the Newtonian potential to G00, and using that, then we'll be able to derive the redshift. So that's the next topic. I should probably, I think there's no point in starting on it now. We'll do that next time. Let's see that we can take questions. And also, if anyone came in late and didn't get their homework back, there's some homeworks here. Oh, this is yours, right? Yes. Is there a question?
So that specific problem of photon redshifting, say if you emit one at the top of the building, so that you can work out